Hello everyone. In this video, we'll be learning about importance of PAC learning, and we'll be also learning how a model can be evaluated. So the full form for PAC learning is probably approximate correct model. So why we need to have this model, okay, and why we need to, what is the correlation with respect to the machine learning technique? PAC learning, it is a framework that is used in machine learning. So mainly it helps us to define the conditions with which a class will be able to learn from the target function effectively. So say, for example, you have some collection of instances about the different features of the fruits and how, under what condition, the hypothesis that you're using will be able to learn a target function. Okay, so like based upon the input features, maybe the color and the shape of the fruit, you classify whether it is an orange or an apple. So, but this requires two important things like one is high probability. So the model should be able to do the prediction more likely. So such that the difference between the predicted and the actual value is minimal. Okay, so the hypothesis that is produced by the learning algorithm is approximately correct. So meaning that it is having less than sigma, that is epsilon. Okay, so which has a very less error. That is the difference between the actual and the predicted value is very less. So what is the meaning of probability? Probability, it refers to the likelihood that the learning algorithm will succeed in finding a good hypothesis. So hypothesis, it belongs to the hypothesis class. Okay, so but then there could be like if you take simple linear regression, the line can be of different slopes, but we'll be able to find one as a best fit line such that the sum of squared error is minimal. So it means that it gives a very high probability. The probability of getting the error is very minimal. So say for example, this is probably is defined by the mathematical parameter delta, where 1 minus delta, it represents confidence. Okay, so how many number of times? So say for example, if delta is equal to 0.05, then 95 percentage chance that the algorithm performs well. Okay, so and the failure rate is only 5%. This is called as probably. The next term is called as approximately. Approximately, it refers to how close is the hypothesis to the target concept function. Okay, so target concept is the actual concept that will be able to classify between the two different classes, positive and negative. So the error of the hypothesis should be allowed within a certain margin. Okay, that is called as epsilon. So if epsilon is equal to 0.01, okay, so we see that the error is just only 1%, and the accuracy of the model is 99%. So this is called as approximately. So to understand about probably and approximate, let us consider you are trying to train a model, and which is a binary classifier to extinguish between apples and oranges based upon the features such as the color and as well as shape. So for PAC setting, what are all the terminologies that is needed? You need to have an hypothesis H. It could be a linear classifier and a target function. Okay, so for target function, it is the function that maps feature to either of the two categories. Okay, so function is what is the instance, that is the input that you take, Based upon the values of the input, you do the mapping either to apple or orange. And the goal is to find the hypothesis such that the error is less than or equal to the epsilon. Okay, that is the error limit with the highest probability. And the learning process, say for example, you are consider there is a model and you're going to train your model with 100 samples of apples and oranges. So in that case, the classifier, if it is achieving 95 percentage accuracy, then the error is just only 5 percentage. Okay, so we see that, and there is less than 5 percentage probability that this performance would have been occurred by chance. Okay, so 95 percentage would be the accuracy and epsilon 5 percentage will be the error rate. So since epsilon is 5 percentage, the error is 5 percentage, then the probability of failure must be less than 5 percentage. So this we can understand with the help of an example. So say for example, you have the height and the weight of m different individuals, and you are going to train your model on this given data set. And the model has to predict whether the person is a fit person or not. So if you would like to produce an algorithm in future that will be able to correctly answer based upon the pair. So say for example, this is the actual, C is the concept, okay, which is the actual boundary, okay, and based upon the height and the weight of the person, based upon the box aligned hypothesis, or those data points that are lying within the hypothesis, we consider as positive, and those data points that are outside the bounding box, that we assume it as negative. And say, for example, you are trying to find a hypothesis which is represented by the yellow box. Okay, and whatever this portion that is the rectangle which is shaded in green, okay, this is the actual concept. So in between these region, we have the misclassification. Okay, so this green shaded region, actually, according to the hypothesis, it is positive, but according to the concept, it is positive. But as per the hypothesis, this is classified as negative. Therefore, it is false negative. And the region which is shaded as yellow, okay, according to the concept, okay, and this is the boundary region, and all those points only within this box is positive. Anything outside this green, it is negative. So according to the concept, it is negative, but according to the hypothesis, this region is considered as positive, which is a misclassification, and hence this is a false positive error. So we are trying to find an XOR operation, that is the probability of concept XOR this hypothesis, that should be less than or equal to epsilon, okay, which is the error limit. So the goal is to achieve very low generalization error, but with the high probability. Okay, so the probability of getting the low error must be so high. Okay, so how many number of times based upon your training your model, the number of times you are selecting the subset of instances in order to train your model, and it should have more probability in achieving low error. So that is the reason it is mathematically represented as probability of the error of hypothesis must be less than or equal to epsilon, and which in turn must be greater than 1 minus delta. Okay, so that is the probability of P of C XOR H must be less than or equal to this epsilon, that is error limit, with a greater probability. So say for example, we have the collection of instances, we have the height and the weight of the person, and based upon the data set, and you want to classify whether the person is um, belongs to the fit category or the person belongs to the obese category. So in order to train the model, we are selecting the different types of instances. Okay, so say for example, you are considering 10 different instances are randomly selected and the model is trained. And after training, you evaluate the performance and try to capture what is the error value that is recorded. So understand, let us assume that this is the hypothesis H1, and for these are all the randomly selected data set. Okay, so we have randomly selected some subset of instances and we have trained the model. Okay, so after training the model for each and every instance, so say for example, for the first subset of instant, the error that is produced is 0.04. For the second, it is 0.03. And it goes till the different subset of instances that we have chosen in order to train the model. So let us assume, okay, this is assumption. Let us assume that epsilon, this is the error limit, and the probability value, that is delta, is equal to 0.20. So according to the formula, so first we need to calculate what is the probability of H1. Okay, so we see that for if you consider the first value, okay, if you take up the first instance, so you take 0.03, which is less than the error limit 0.05, and 0.03 is also less. But 0.9, we see that this is the error is too greater, and 0.06 and 0.025, this is less than the given error limit. And every other value, we see that the value is less than the error limit. So out of all these subset of instances, okay, so if you take 3, 4, 5, 6, 7, 8, 9, 10. Okay, so out of 10 different times, we see that 8 times the model is able to get a good accuracy with a lower error rate. But 2 times it had failed. So what is the probability of H1 is 8 divided by 10, which is equal to 0.80. So now what we need to compare, we need to put it in the formula 1 minus delta. That is the probability. Okay, so whether the calculated value, whether it is greater than or equal to 1 minus delta. So what is 1 minus delta? 1 is 1 minus 0.20. 1 minus 0.20 is equal to 0.8. So what is the answer we have already got? The calculated value is also 0.80, which is greater than or equal to the calculated value, which is equal to 0.8 is the probability value. And the probability of H1 is exactly 0.80. So since the condition is satisfied, then we can conclude that H1 is probably approximately correct. So if not, then we can conclude that H1 is not probably approximately correct. So if the calculated error bound, so if the probability of the hypothesis, if it is greater than or equal to 1 minus delta, then we can conclude that it is probably approximately correct. So let us assume that you're taking another different hypothesis and you are randomly collecting some different set of samples and you're training the model and you're evaluating the performance. So at this time, let us assume that these are all the error value that is recorded, and the error limit is 0.05, and delta, the probability value is 0.20. And when we compare all these value, okay, so how many times the model has failed? Okay, so we see that 0.06 and 0.059, 0.55. So in all these value, we see that the error rate is too high. Okay, so which is 6%, 5.9, 5.5. Okay, but every other value we see that which is less than the error limit. So how many out of 10 times, how many times the model has failed? Okay, so the probability is out of 10, 7 times it was able to get the error predicted value, which is less than the error value, which is 0.05, and 3 times it had failed, which is 0.70, and 0.70, we see that the value is less than 0.8. So then we can conclude that H2 is not probably approximately correct. So the importance of the PAC learning, mainly it is used to help the algorithm generalize well from a limited set of samples. Okay, so this will be able to do the prediction for the unseen data. So this is also widely applicable, and it serves as the basis for analyzing and designing various machine learning algorithm. And it also guarantees the way it is so crucial for assessing the reliability and the robustness of the algorithm. So by understanding the PAC learning, researchers will be able to create more effective models, okay, that will be able to do the predictions. So the core concepts of the PAC learning, okay, so from this what we can understand, we'll be able to find what is the best number of samples which is required in order to achieve a good accuracy and with a greater confidence level. So this ensures that the hypothesis will be able to generalize well to the unseen data. So what are all the most important factors to consider if you want to get a higher accuracy with the higher confidence, especially when you work on with the complex space, we require more number of samples. Then what would be the approximate correct mathematical formula that is needed? Okay, so just you need to have a trade-off. Okay, so when you have a larger and a complex hypothesis, we see that there is more risk of overfitting. It will learn too much from the training data set, including it will capture the noise. Okay, but it will fail to do the prediction for the unseen data. But when your hypothesis is very smaller, very simple, okay, and we see that it is very less flexible, okay, but it produces underfitting. Okay, so it is not able to perform good for the trained data set and as well as for the unseen data set. So this is about this PAC learning, and it helps us in the generalization. And generalization is quantified by the probability that the hypothesis will have a low rate on new samples. If the model is able to generalize well on with a low error rate on the new samples, then it is great. And what are all the key points? Most important thing, what is the mathematical expression behind this PAC learning is this is the correct formula that is used in order to calculate the sample size where m greater than or equal to 1 divided by epsilon and log of 1 divided by delta plus Pc of h. So where m is the sample size, epsilon is the desired accuracy, and delta is the confidence level, and VCH and this is the VC dimension of the hypothesis. Okay, so the maximum number of data points that can be shattered correctly in all possible ways. So this is about your PAC learning. Okay, so you have to understand why PAC learning is used in order to enable the ML model to get a good accuracy with a low error rate. It also helps us to calculate the total number of samples that is needed that can make the model more effective. So with that, we can conclude the lecture for the PAC learning, which is probably approximate correct model.